We're going to do another example now. I don't know why that's so thin. And this one's going to be a little bit more complicated. We'll probably have to split it up into 2 videos. So actually, let me start a stopwatch so that I don't run too long. Okay, so this is kind of a word problem too. Consider a container given by 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, and 0 less than or equal to z less than or equal to 1. It's a box. And we're going to place a plate in the container. And the graphical description of where that plate is given by x plus y plus z equal to 1. So then if we wanted to draw a picture of this, I should have done this beforehand. I'm sorry. Here's 1, here's 1, here's 1 in x, y, and z. So the space we're thinking about is this box. Just imagine that that's really a box and not messed up. So we're imagining this box where x, y, and z have to fall between 0 and 1. And then inside that box, we have a plate that uses the plane here we go. X plus y plus z equals 1. So here's like the line x plus z equals 1 where y is 0. Here's the line z plus y equals 1 where x is 0. And here's the line x plus y equals 1 where z is 0. And so this kind of like triangular wedge is the plate sitting inside the box. This idea of taking y, x, and z equal to 0 to draw the bounds of the plate is something that you'll get a lot of practice with in the next exam. But for now, just that's an easy way to plot things in 3D is I go back to my idea of how I plot things using only 2 dimensions. So let's see. The container is heated. So that the temperature at any point is T of x, y, z equal to 4 minus 2x squared minus y squared minus z squared. And that's in hundreds of degrees Celsius. So apparently it's very hot. And we want to find the hottest and coldest parts of the plate, where cold is a very relative term. So this is a constrained optimization problem. The thing that we're trying to optimize or maximize or minimize is this function t. The constraint is you have to live on the plate because that's the only thing we care about the temperature of is this metal plate that lives in this box that's temperature controlled in a very special way. I want to point out that when I gave you these steps, I told you to solve z equals f of xy. This was for like 2D optimization problems because most of your examples are going to be 2D, but the steps actually do work for z. It's just instead of 3 equations with 3 unknowns, you get 4 equations with 4 unknowns. So we're going to do that in this example. All the steps are the same. It's just this is a little bit harder and more algebra, so we do it less. So I'm going to identify what I just wrote here. Thing to optimize is t. And so I'm going to go ahead and rewrite that as f, just because that's what we've always done. So f is 4 minus 2x squared minus y squared minus z squared. It's 4 minus 2x squared minus y squared minus z squared. And my constraint is that x plus y plus z equal to 1. Yep. So my g is everything that's not a constant number, x plus y plus c, and my c is 1. This is that first step. Get everything in order so that you know what to do. And next, I'm going to start calculating gradients. So my grad f is minus 4x minus 2y minus 2z. That's partial derivative with respect to x, y, and z. My grad g is 1, 1, 1. Usually these will be pretty simple just because you have to solve an algebra problem, and you can't if it's too complicated. And so the equation to solve is grad f equals lambda grad g. That is, I need minus 4x minus 2y minus 2z equal to lambda times 1, 1, 1, which is just lambda, lambda, lambda. So that gives me a system of 3 equations. I'm going to have minus 4x equals lambda, minus 2y equals lambda, and minus 2z equals lambda. I'm just going to check I copied that down. Minus 4x, minus 2y, minus 2z. X, Y, Z. Okay, all equal to lambda. I have 4 unknowns, x, y, z, and lambda. So that tells me I don't have all the equations I need yet. And the last equation is always just your constraint. X plus y plus z equals 1 is our constraint for this problem. And I'm going to go ahead and start trying to solve stuff. So I'm going to look at these two first. So I've got minus 2y is equal to lambda. That's what 1 tells me. So lambda is minus 2y. 2 tells me minus 2z is equal to lambda. But the first one told me the lambda is minus 2y. So that means minus 2z is minus 2y. That tells me z is equal to y. Okay. Now I'm going to go ahead and do this one, I guess. So I know minus 4x is equal to lambda. And I just learned how to get rid of z in terms of y. So I'm going to try to get rid of x in terms of y. So I'm going to plug in that first thing I found again right here. And that's going to tell me minus 4x is equal to minus 2y. Or x times 2 is equal to y. So that means x is equal to 1/2 times y. And now I can go to my fourth equation. X plus y plus z should be equal to 1. But I learned what x and z are in terms of y. So I know that x is 1/2 y is y, and z is y. So that's 2 plus a half is 5 halves. Let's see, 2, 4, 5. Yep, 5 halves y is equal to 1. So that tells me y is equal to 2/5 when I just move over the 5 halves. That means x is equal to 1/2, y is equal to 1/5, and z is equal to y is equal to 2/5. So the only point that satisfies the system of 4 equations is going to be 1/5, 2/5, 2/5. And I know we're sitting right here past 10 minutes. My stopwatch is telling me. I'm just going to point out. Did I draw my pic? Here's my picture. 1/5, 2/5, 2/5. I don't know. That's somewhere like right there on the plate. We're going to continue with the rest of the problem in the next video.